So now we want to spend a bit of time talking about sets. So this is probably one of the first things that you'll see in your probability theory classes because probability works off of sets, right? So you basically find the probability of a set or a subset. So we, of course, at this point should be familiar with set notation, right? So like maybe using the most recent stuff we did as an example, we could have the set of x and y points such that x is between 0 and 1, y is between 0 and 1, right? So pictured, this would be all of the points in this little square right here, right? And we write it this way because there's an infinite number of points here, so we can't actually write them all out. We could just have a finite set, right? Maybe we just have s is equal to 1, 2, 3, 4, 5, right? This is very common in probability where your sample space is a finite number of things, like heads or tails, something like that, right? And of course, we saw the sets of the natural numbers, the set of integers, set of real numbers. Those are all different types of sets as well. So this is kind of like the space that we live in the context of probability. So that's why I want to spend a little bit of time talking about it. And even outside of probability, this is very important just for anything involving functions, because functions are maps from one set to another set. And we're going to look at that in a little bit more detail too in the coming days. I mean, functions, of course, that's pretty much, that encompasses kind of everything we're doing, like any kind of probability distribution function, or, in statistics, you have your likelihood functions. So you can't get away from those. So let's go ahead and start with just a few definitions that should be kind of familiar, maybe not formulated this way. So let's let A and B be sets. So then we can make some new sets out of this. Like we could make the intersection of A and B, for example. So we say A intersect B. So this is going to be the set of all the points x in U, where U is going to be some universal set. So let's say let A and B be sets such that A is in U and B is in U. Okay, so I've mentioned this symbol before, but this is kind of like a sideways U, and it is similar to how we write like this one right here where we say X is in a set, except this is saying that an entire set is contained in the other set. So every point that's inside of A is also inside of U. Okay, so this is a very important relationship here. I'm going to write that down as its own definition, actually, now that I think about it in a second. But first, let's finish this one. So A intersect B will be all of the X in U such that X is in A and X is in B. Okay, so we have the and here. Right. So of course, this is probably something you already know, working with intersections before, but this is a way to formulate it in terms of another set. So we write this as its own set. And we call this, of course, the intersection of A and B. So I'll just write intersection here. And then we also have the union of A and B. So this is going to be A union B, which is the set of all X in U such that X is in A or X is in B. Okay. And these are very important sets. They come up a lot when we're making different combinations of things. Something like Bayes' theorem, for example, very important theorem. The heart of an entire field of statistics called Bayesian statistics relies on that theorem. And this is seen in that theorem. Just something as basic as calculating OR probability uses these, right? So they come up all the time. Let's go ahead and write down those. Let me say this is a definition here so we can organize this a little better. This is a definition here. Now another definition here. Okay. So we say A is contained in U written A contained in U. I don't think that this sideways U, I'm sure it has a name. I don't know the name of it off the top of my head. I don't really hear the name referenced. If X in A implies that X is in U. So in other words, any X in A means that that same X must be in U. Okay, so all of the points in A are also in U. So this doesn't necessarily work in the other direction. But this is very important because, actually I'll just write this as its own definition. We say two sets A and B are equal if A is contained in B. Now, if there's a possibility that the sets are equal, we put this line underneath it, similar to like if you had less than or equal to or something like that, right? I didn't do that here because it's kind of implied that U is like a larger set and, you know, that A is not equal to U. But if there is a possibility of equality, we write it like this. And B is contained in A. Okay. So this is very important because if we want to show that two sets are equal, you have to show that both of these things, that if that A is contained in B and if B is contained in A. And we'll do some of those in the next video where we talk about proving set relationships. But this is typically what we mean by equality of two sets. So in other words, any number in A or element of A, it doesn't have to be a number, is also in B. And any element of B is also in A. So a few more important definitions here. Other things that I've kind of referenced before, a set difference, or also sometimes called a relative complement. And we'll look at the complement in a second as well. Okay, but the relative complement, this is A minus B. So it's sometimes written like this, or it's sometimes written like this, A backslash B. So these are the same thing. So this is equal to X in U such that X is in A and X is not in B. Okay, so you take any element in B and you kind of subtract it out of A. Right, so that's why we use this notation. So I used it before when referencing R minus 0. Okay, so this is all the real numbers except for 0. So that's what this notation means. It's just the single element with 0. You could also write it as R backslash 0. That's fine too. And then of course we can have the regular complement. Okay, so definition here. The complement is it's usually written with a C superscript, but there's a lot of different ways to write this that you'll see. So some common ones I've seen is that you put a bar over it. We don't typically like to use that in probability or statistics, you know, in the higher level classes. The bar, you know, a lot of times that's used for sample mean, which, you know, wouldn't be that in this context. But there's also this idea of the closure of a set. So this is usually reserved for the closure of a set, which is very different. The closure of a set is if you take an open set, then you bring in all of the endpoints basically. So like if you had the interval 1 to 2, the closure of that would be 1 to 2, right? So you won't see this one very commonly, but in the lower level probability classes, this is how it's, I've seen this symbol used a lot. I've also seen A prime used somewhat often, which I also don't really like. When we're talking about matrices, that's typically reserved for the transpose. But it's also typically used for derivatives. And, it's also just kind of used as like a index. Like if you want to use a different set that's like similar to one, but you don't want to come up with another letter, sometimes you call it A prime. So for that reason, we don't really use that one too much either. So I would stick with the C notation. That's all I'll use. But anyway, so the A complement. So the definition of this would be X in U such that X is not in A. Right? So all the points outside of that set. Okay. So some other ones, that I've kind of already alluded to, subset. Right? We say A is a subset of U if A is contained in U. Contained or equal to U could still be a subset even if it's equal. And we say it's a proper subset if we have A contained in U without any chance of equality. So a proper subset means it's definitely a subset, right? It's not necessarily the same set. But even if two sets are equal, one of the sets is technically a subset of the other one. Okay. So what if we had that U is equal to 1, 2, and 3, and we had that A is equal to 1, 2, and 3. Okay. Then what is a complement? Okay. So a complement would be all the points that are in U such that they're not in A. But here we don't have any because all of the points in U are also points in A. In other words, A is equal to U. So a complement would be what we call the empty set. So a complement is equal to the empty set. Okay. Well, we don't normally put the set notation around it. So it looks something like this. So typed, it looks just kind of like a 0 or an O with a diagonal line going through it. Sometimes you might see it written like this. So in other words, the set brackets, but with nothing in them. But typically it's just referred to as this, the empty set. This is important in probability, because probability of the empty set is 0. And sometimes, that ends up being your sample space as the empty set. So a couple more things I want to discuss before we move on to the next video where we talk about proving some of these set relationships. So I'm just going to say a couple things without writing them down because they're just something to be aware of, not necessarily something we need to know here. But the power set is sometimes referenced. The power set is the set of all subsets. So the power set of A would be the set of all of the different subsets of A. So a set, the members of the set could be another set in itself. So I guess I will write something down here. So the power set, if A is equal to, say, A, B, then the power set of A, and it's hard for me to write this exactly. It looks like probability of A. It's like I guess kind of a cursive P. I'm not exactly sure what symbol it is. I don't think I've ever typed it before. But this would be equal to all the different subsets you can make out of A. So that would include the empty set. That would include A. That would include B. And that would include the entire set, A, B. Okay. So in general, if a set has n elements, then its power set will have 2 to the n elements. So here A has 2 elements, so the power set has 2 to the second elements, which is 4, which is exactly what we have here. Okay. Now, another thing you sometimes see mentioned in regards to sets is cardinality. Cardinality is basically a measure of a number of things in the set. So for a finite set, that's just the number of, elements. So like the cardinality of A is 2, the cardinality of P of A is 4. But for infinite sets, it gets a little bit tricky. So it actually, I think it's really interesting. What if we think about the natural numbers? Okay. And what if we think about the even natural numbers? So we don't really have a special symbol for that. Let's just write evens. Okay. So it's going to be 0, 2, 4, 6, etc. What do we notice about these two sets? Well, if we took every number in this one and we just multiplied it by 2, okay? So all we do here is we multiply by 2. Then we create a perfect map between these two sets, right? So just take every natural number, multiply by 2, and all of a sudden you have all the even numbers. Now, when we multiply the elements by 2, we're not changing the number of elements. So it stands to reason here that these have the same number of elements, okay? Which is kind of, at first glance, it's kind of a paradox, right? Because we're saying that the set of all natural numbers and the set of even numbers have the same number of elements, right? So this is where cardinality can get pretty tricky when we're talking about infinite sets. And these sets do have the same cardinality. So we do regard them as having the same number of elements. So it's a bit tricky. Not really something we're going to look at a lot, but just something kind of neat to think about. If you get into like measure theoretic probability, which is, beyond the scope of the probability theory class, more like a PhD level probability class, this becomes very important. Because basically any set that is what we say countable, which would be something like this, or even up to the rational numbers, probabilities on those sets are usually 0 if we're talking about like continuous variables. So basically any countable set has the same cardinality as the natural numbers, which again is more of a neat thing than something we're going to really look at. Technically, the definition is that if you can make a bijection between two sets, we say they have the same cardinality. We're going to look at bijections later, but basically it means that you are able to create like a one-to-one, and which we've already seen what a one-to-one function is, and an onto function, which is what we'll look at. But just multiplying by 2 definitely fits that criteria.